We will now go through several examples. Example 34.1. Light is incident at angle θ1 on the boundary between two transparent mediums. Some of the light travels down through the next three layers of transparent materials, while some of it reflects upward and then escapes into the air. A. Physically interpret the refractions for this diagram. B. Determine the values of θ5 and θ4. Let's physically interpret the graph first. What we know here, as light goes from a lower medium to a higher medium, the ray bends towards the normal. If I go from a higher medium to a lower medium, the ray bends away from the normal. Let's check this with the graph. So if I look at the incident ray at θ1, this is the direction of the ray, and if you look at the normal, the ray has bent down towards the normal as it goes into medium 2. This is the direction of ray 2, and you could see as I go from N2 to N3, I'm going from a higher to a lower, so it bends away, and then finally, in the last medium between 3 and 4, you could see that the ray has bent towards the normal. Summarizing these results, here's what we get. So now we move on to B, where we want to calculate the angle θ5 and θ4. Calculating θ5. Here's an image of where θ5 is. So we find here that the first ray from index 1 is reflected and then it refracts back into air. So looking at these angles, note that the normal in both of these situations are the same. Because they're the same, what we find here is that we will always deal with the sign of the angles. If the normals were perpendicular, you'll find here that we'll have to go towards cosines. So if I look at this thing here, we know by the law of reflection that this is θ1, and this other angle here should also be θ1. So if I now apply the law of refraction at this point right here between N1 and air, this is what we write. So Snell's law of refraction says that N1 sine of θ1 is equal to N air sine of θ5. Solving for θ5, we do some basic algebra. So θ5 is 56.9 degrees. Next, we solve for θ4. Once again, note that all of the normals are in the same direction. As a consequence, we can apply consecutive Snell's laws to these four medium interchanges. That is, we can write N1 sine θ1 equals N2 sine θ2, N3 equals sine θ3, N4 sine θ4. In other words, I don't have to solve for θ2 or θ3. So what I can do then is that I can actually just ignore these guys and solely focus on solving for θ4 by knowing the information at medium 1. Let's go do that now. Applying the same algebra as before, we find here that θ4 is equal to 35.3 degrees. Let's move on to the next example. Example 34.2. The prism has a refractive index of 1.66 and the angles A are 25.0 degrees. Two light rays, R1 and R2, are parallel as they enter the prism. What is the angle between them after they emerge? First thing that you have to note here is that there's symmetry between ray 1 and ray 2. So by only focusing on ray 1, we automatically will know what the angle of refraction is for ray 2. So I'll only focus on ray 1 to begin with. Let's draw this out. So looking at this prism here, I have ray 1 coming in, and note that because this angle here is perpendicular, right here there is no refraction, and the beam continues to move in a straightforward manner. When we have this beam interacting at this point of refraction right here, now I have to pay attention to the normal. Let's draw that out first. At this point of refraction, the ray will now bend. Let's draw that. Now, what is the angle that this ray emerges? We have to talk about this relative to the center part. So this angle right here, which I'll call beta, is the angle at which the ray emerges from the prism. This is the angle that we need to determine. So to focus on that angle, note that I can draw a triangle, this red triangle, and what you're seeing here is that we can use Snell's law to figure out two of the angles. And there's going to be two angles that we don't know what they are. So let's write those into detail. As light comes in, we could see that ray 1 will come in at incident angle theta 1. Now, since I'm going from a higher index of refraction to a lower index of refraction, we could see that this ray bends away from the normal at theta 2. But there are other angles that we need to figure out. Note that we don't know this angle right here. We don't know what this angle is right here. And for the sake of argument, which is going to be important for us, I'm going to define this angle as alpha. Now that I defined the angles, note that this red triangle must all have the sum of the angles to be 180 degrees. Knowing that this is a 90-degree angle, we know that this relationship to determine beta then must look like this. So now that I have the relationship to determine beta, now I bring in the angle of 25 degrees and then work my way around as follows. We are given that the first angle here must be 25 degrees. Since the sum of all these angles must be 180, and I know that this is 90, that means that the sum of this angle and that angle must be 90. In other words, I know that 90 degrees plus this mystery angle tells me that this mystery angle must be 65 degrees. So I can write this as 65 degrees. Because this normal line is perpendicular to the green, you could see that the sum of 65 plus this angle, theta 1, well, that sum must be 90 as well, so that immediately tells me that theta 1 must be 25 degrees. As I continue to move around, again note that this angle right here is a 90-degree angle here, so therefore this tells me here that this must be 65. And if I look at the normal relative to this, that means that this angle here must be 25 degrees. So if I go back to the relationship to determine beta, we can then summarize it as follows. From this relationship, you could see here that the only thing I gotta solve for now to get beta is alpha. And the way we do that is that if I know that this angle here is the angle of refraction, if I calculate theta 2, and I know that this angle right here is 90 degrees, then theta 2 plus alpha is going to be 90, and therefore I could solve for alpha. Let's do that now. Applying Snell's law to get theta 2, we write, now solving for theta 2, we get an angle of 44.6. Now solving for alpha, we get that alpha is 45.5, and finally we can solve for beta. Therefore, the angular spread of the beam is, with the angular spread of 2 beta, we get 39.1 degrees. That is, as ray 1 and ray 2, when they diverge after crossing, this width between these two is 39.1 degrees.